Hello and welcome to this video on linear regression. We will look at the data we have at hand, on which we will try and fit the linear regression model in R. We have a column month ranging from April 2014 to September 2017, cost of advertisement and sales. Along with that, we have team size and whether it is a festive month or not. The company wants to analyze the impact of ad cost on its sales. The regression model will help us understand the kind of relationship that exists and whether ad cost significantly impacts sales or not. Other factors such as the team size of salespeople and whether the month was a festive month or not might also be crucial factors in determining the sales of the company. Let us therefore see what all we will do in this video. First, we will draw a scatter plot and fit the regression and the mean line to it. Then, we will perform a regression analysis on the data. After that, we will interpret the output of the model. Then, we will predict the sales of a particular month where advertisement cost is 400. We will then prove that the sum of residuals of a linear regression model is 0. Finally, we will draw the residual curve and the normal QQ plot. Let us go to R and open a new script. We save this script first. We will import the dataset we just saw in R. We have already seen various methods of doing so. Here, in this method, kindly ensure that the Read Excel package is activated. We name the data as reg data. We can see that the data is in front of us. We will now draw the scatter plot for the data. This is a part of the exploratory data analysis where we will try and understand the underlying patterns or trends in the data and if there are any significant errors that we can see or not. We write P is equal to ggplot. Please ensure that the ggplot2 package is enabled or activated. We give the name of the dataset reg data. After that, we provide the aesthetics in which we provide the variables to be plotted on the x and y axis. On the x-axis, we want ad cost and y-axis, we have sales. We keep the color to be red. As we execute P now, we can see that we have the basic outlay for the plot. Now we will add layers on this plot to depict the relationship through a scatter plot and other methods. So we write P plus geom point. The moment we press Ctrl plus Enter, we can see the scatter plot on the bottom right of the screen. We zoom into it to see the plot. As expected, we can see an upward slope or trend in the plot implying a positive relationship between ad cost and sales. Thus, as the expenditure on advertisement increases, sales are expected to rise. Next up, we fit the regression line to this graph. So we add another layer to this code by writing stat smooth. The moment we execute this, we can see a line going through the scatter plot. However, this is not a straight line. To get it to be straight, we put the method to be equal to LM, which stands for linear model. Now we can see a straight line is drawn in front of us. The dark gray region around the line signifies the confidence interval. As we know, the regression line is also called the best fit line. The next thing we will draw is the mean line. This is also called the average line. Let us first calculate the mean of sales and save it in a variable x. It comes out to be 23092.86. Now we will add another layer to the plot P, which is geom h line, and in brackets we will give y-intercept equal to x, which is the mean of sales. As we press Ctrl Enter, we can see a black line going right through the plot. It marks the average value of sales for the given data. Similarly, we can draw horizontal lines showing the minimum and maximum values of sales too. These lines would then help us understand more about the data of sales for given levels of advertisement cost. The minimum line, maximum line, and other such lines can help us find various statistical properties about the metric. Now that we have plotted the scatter plot, mean line, and the regression line, we will move on to the regression model. We name the model as M1 in R. The function we use here is LM, which stands for linear model. The first input is the formula for the model. We have sales as a dependent or response variable, followed by a tilde sign, after which we give the explanatory variables, which is ad cost for us. Then we give the data from which we will prepare the model, which is reg data. As we press Ctrl Enter, we have created the model. The moment we execute M1, we can see we get the intercept and the coefficient of the formula. A positive coefficient indicates that there is a positive relationship between sales and ad cost, which we saw earlier through the data visualization as well. There are various methods in the LM function in R. To check for them, we write methods and class equal to LM. On the right, we can see the various methods which can be used in the LM model. Some of them are ANOVA, confidence interval, log likelihood, among many. Let us find the summary of the model created to get more insight into it. As we execute the command, we can see a list of metrics on the right. First up is the model, followed by information on the residuals, such as the first quartile, minimum value, median, maximum value, etc. Then we have the estimate for the intercept and the coefficient and their respective standard errors, Z values and P values. The fact that there are 3 stars shown next to both the intercept and the coefficient, it means that both these values are statistically significant. We can also ascertain that from the fact that they have really small P values. The residual standard error with 40 degrees of freedom is also available. The R-square value of 0.8993 tells us that 89.93% of the deviations in sales are explained by ad cost itself. Adjusted R-squared value is also given here, which is quite useful when we use more than one variable. Only if the adjusted R-square increases by the induction of a new variable does it make sense to have it in the model. F statistic of 357.1 is large enough to reject the null hypothesis that sales and ad cost are independent of one another. Next, we find the ANOVA table for the M1 model. We can see the results of analysis of variance here. It gives us the degrees of freedom, sum of squares, mean sum of squares, and finally the F value, which is the same as before. Let us see what all things we can get from this model. We write names M1. As we execute, we can see a list of metrics or variables shown on the right hand side of the screen. Let us have a look at a few of them. The moment we write $M1, we can see a drop down of these terms. If we select coefficients, we can see the value of the coefficients in the model. If we type $M1 residuals, then we will get the value of each residual in the model. Then we see $M1 effects. Next up, we have the fitted or predicted values of sales for the given value of ad cost in the model. Lastly, we write M1 model, which will give us the ad cost and the respective sales value based on which this model was built. Now that we have built the regression model and also analyzed it, we can input the value of ad cost to be 400 in the model and calculate the predicted value of sales with the given estimates of the intercept and the slope. It will be minus 6845.95, which is the intercept's estimate, plus 400 into 77.28, which is the slope. The estimated sales figure will come out to be 24066.05. Next thing that we will do is prove that the sum of residuals is equal to 0. These are the actual figures of sales for the given level of advertisement expenditure. Now we will calculate the predicted values for each level of ad cost and then find the difference between the actual and the estimated or predicted values. The difference between them will be the errors or residuals. To get the fitted values, we write y is equal to fitted values of M1. As we execute y now, we can see that the fitted values for different levels of ad cost are in front of us. We convert this into a data frame. Let us copy and paste these values in Excel. Let us go to data and convert this text into column. These are then the predicted values of sales. The difference between the actual and the predicted value is then calculated to get the errors or residuals. We can do this in R by using the residuals function. We will save it as a data frame. Residuals can be seen in the console. The values in Excel and R are the same as expected. Please copy the residuals from R to Excel in the same way as we did for the fitted values. We then find the sum of the residuals and see that it comes out to be 0 as expected. In R, we find the sum of Z. We can see that this number is nothing but 0. Lastly, we will make the residuals curve and the normal QQ plot. We write plot of M1. As we press return, we can see the residuals curve in front of us. It is called the residuals versus fitted plot. It helps us see if there is any relationship or trend between the fitted values and the residuals or not. Ideally, there should not be any, since the residuals are completely random in nature. Also, the variance across all the values of residuals seems to be the same, which indicates that the variance of residuals is constant, which is another assumption in the classical linear regression model. We can export this curve in the PDF format from here. If we press again, we will get the normal QQ plot. QQ plot helps us ascertain if the residual values follow a normal distribution or not. The plot here does indicate that the residuals seem to be normally distributed. As we keep pressing, we can see different plots in front of us. The scale location one shows us that the variance remains relatively unchanged as the fitted values change. We press again to see the last one. So basically, this will give us 4 types of graphs or plots for the model. This one shows that the outliers do not have a huge impact on the regression line. This is how the linear regression model works in R. Thank you.